It's the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we welcome you back to episode number 98, where today we are finally adding another episode in our collection of astronomy episodes, where today we're talking or continuing into astronomy part 4. So just a little astrophysics. A little
bit of
intro
astrophysics.
to astrophysics. Interestingly enough, because our class, our third year astrophysics class, the very last course you can take in university relating to astrophysics. Undergrad university is called Intro to Astrophysics.
That's right.
So it's still an intro.
This is going to be an awesome episode of the podcast, especially because this is my specialization.
Yes, it is.
It's kind of the one thing that I majorly, I'm not studying it specifically per se, because you're doing like everything that I'm doing related
so far,
to
right?
astrophysics.
Next year you're going to be crazy,
next year
though.
will be different.
Next year you're going to be.
I will have like a independent research class and also maybe an independent study class in astronomy / astrophysics. So that's going to be really cool.
Mm-hmm.
But that's all that I have left to do relating to astrophysics.
That's
Cool. This year we're taking Intro to Astrophysics. It's a theoretical course. We're also taking an experimental astrophysics course, which is also really cool. We're going to get to talk about the labs that we will have done in the future when we're done with the class in about 2 months.
That will be a really cool episode because we are doing some very interesting labs, like literally like determining the radii of planets based on stellar brightness levels, and that's the kind of stuff that you hear about in a research paper, and we're doing it. So it's pretty cool.
Yeah,
very excited about that
for sure.
And so this is the last theoretical astrophysics course, right? So this is kind of gonna be like our culmination of what we've learned.
Mm-hmm. And it's such a cool class.
It is
so cool because last year we took the two astrophysics courses that you would take if you're doing if you're going into astrophysics,
or even if you're minoring. But
I was gonna say major, but also the minor.
Yeah, you also the minor.
And those two courses, basically, the first half you go through stars and planets, and the second half is galaxies and cosmology, and that would take up a full year. But this year we are taking one semester of astrophysics, and it goes through everything, but it goes through so much more math
in detail.
So much more detail.
Much more detail. See, I think I was actually thinking about this, and I think every future part that we do to any real standing episodes series, like quantum mechanics or like astronomy, for example, is all gonna be similar material, but just more detailed, because that's really what we're doing, and that's how we're learning it too.
Actually, I think the next astronomy episode that we do will be more cosmology, because we're going to get to
that's what I'm
soon,
saying.
right?
If we have guests, obviously, that's a different story.
Yeah.
Then we can definitely dive into some crazy stuff. But if we're just talking about it ourselves, it's always just going to be learnings from class or some kind of advancements that we've done. Because again, as you very well described, this semester is, it basically talks about a lot of stuff that we did last semester, just really honing in on the theory, really getting in the math, the details, the grimy stuff about what's really happening is kind of what we're learning in this particular course. So it's a little cool. I really enjoy it. I think you do too. So I'm very excited to see at the end of this semester, hopefully we'll get to speak to a professor or two about in this class, and then we can really dive deep into what we spoke about.
Yeah. So before we do get into the episode, we have a comment of the week. Today's comment of the week comes from Mantan Patil. They say, "This is my first time watching on YouTube. Just want to say this podcast is really cool." Thank you.
Thank you.
Thank you. I think it's cool too.
Thank you.
That's a very nice comment. If you want to be next week's comment of the week, make sure to come on to this YouTube video and leave a comment, and you might get picked next week. I
did want to mention some news, because we did officially hit 400,000 downloads.
I was going to say that. Yeah,
you're going to say that. Awesome.
400,000 downloads.
So that was a pretty nice milestone. Thank you, everyone, for continuing to download that episode. And road to 500. We're close. We're coming.
Also, we get a lot of nice DMs on Instagram. Thank you, everybody.
Yes.
I will say, if we don't answer, we're sorry. We just have not a lot of time to do like there's just so many like things going on in our lives right now. We will try. I know we've gotten like some emails asking like, how do you solve the time dilation thing around a black hole? And I'm just like, I don't like, I'm interested in what you have to say, but also like, one, I don't know, and two, I don't have a lot of time to like really like conjure up an answer. But we will try to answer everything.
Yeah, so for those people who are watching this first day, you might also notice it's another Wednesday episode.
Yes.
Because it's another one of those.
Yeah, unfortunately, this weekend we were literally waking up, working, falling asleep.
I mean, I was talking to my mom the other day, like in the 72 hours, we were probably working like 60, like counting sleep, obviously. Like I'm saying,
I don't know about that.
I'm saying, obviously exaggerating, but I'm saying like we worked so hard because it was just wake to bed.
Yeah.
We were just writing because we just had so much stuff to do in these courses. So it's just a lot of work sometimes, and add the podcast, it gets hard. So we want to reply to everyone. It's just that sometimes it definitely gets hard. And continuing on before we get into the podcast, the NFT winner that we announced, that actually technically the NFT should have gone up because now
everything's late.
So the next NFT is gonna probably be announced like episode 100.
We'll do it tomorrow.
Like we'll announce the winner episode 100, so that'll be a little cool.
Yeah.
But for this particular NFT, I think this was a really cool NFT because this was like our original logo on the original background, so it was really cool. And Michael Wagner won this NFT. So congratulations. We already DM'd them. They replied. So we're going to kind of get back to them, give them soon. And that's going to be fun.
Actually, something cool that we can do for our next giveaway is we can like plan a live episode or like a live on Instagram and then give it away live.
Oh, that's a nice idea. That's a nice idea. Cool.
So
Why
like,
not? Okay.
So like, make sure to like stay tuned for when we're gonna do the live, because like we're gonna go live, maybe be live for like half an hour.
But we'll announce it though.
No, we will announce it.
We're not gonna just, because I know sometimes we just go live.
Yeah.
Like we won't do that. We'll announce it like, okay, we're gonna do it on this day, and then we'll do it. So that'll be fun.
Yeah.
Actually, that's not a bad idea.
Yeah.
Let's do that.
Okay, everybody, let's go. Okay, first thing, I want to start with this, okay? Because I remember myself being in high school applying for astrophysics, and this during the whole process, I was thinking astrophysics is really cool. Also, I have no clue what you do in astrophysics. Like, if you would have asked me at the time, like, name like one thing that you study, I could have said like stars. But like nothing beyond that. I mean, like I didn't know what a star really was back then.
Valid.
It's a ball of gas, but what does that really mean, right? How do they work? I don't know. I didn't really know anything about astrophysics. So this is for all the people that were like me. What do you learn in an astrophysics course? So here's the outline. And I think it's such a beautiful story that it tells. And same thing goes for what's that course? It was linear algebra. Linear algebra, the course that I took last semester with Dr. Wolski, actually, he was on the podcast twice. The story that course told was beautiful because we started off just looking at like determinants and diagonalizability briefly. And then we went back to starting with vector fields and then going all through linear combinations, linear transformations, all these things, and then ending with diagonalizability and whatever that form, the canonical form and stuff like that. It was such a beautiful story that it told. And the same thing is happening with our astrophysics course. And here's what we're doing. So essentially, in astrophysics, you study things that happen in space. There are a lot of things that do happen. And so it's a pretty broad situation that you have to study. So you kind of have to pick and choose the things that you group together. And so the first thing we studied this year were the equations of state. Now, this constitutes like hydrostatic equilibrium. For example, if you have like a balloon underwater? Is it going to rise? Is it going to fall? If you increase the pressure differential, is it going to rise faster? What happens? What do the conditions need to be for the ball to just stay static in space? You know, you have to deal with, you know, what's the pressure at the top versus the pressure at the bottom. If they're different, then there's going to be a force and things are going to move around. We talk about a lot of different types of pressure because in space, these objects that we call stars are naturally occurring objects. And we just try to explain how they occur and what are their properties. Turns out that, you know, it's not just one thing. There are different types of stars depending on their initial conditions, and the way they evolve also changes depending on how big they were initially, how massive they were initially. Different types of pressures become important in different situations, and we're actually going to talk more about that this episode. So yeah, we start off by talking about just clumps of gases, how to describe the equations that determine the motion of the gas in space.
Also like a clean advantage, I think, of like astronomy is that, well, at the end of the day, you're dealing with things in space. So it's not like on Earth where there are multiple things, multiple factors. Now, it's not like you don't have to take factors into consideration in space, but it's much more like you're in an isolated system, now deal with something. And I just like that, especially like as you were saying, like, you know, you're kind of picturing things now, first of all, also like on a much bigger scale, because like your whole intuition about, you know, distances and sizes is kind of just completely skewed, right, the moment you get into it. Because like we see some stars and some clouds that are like 10 times the mass of the sun, like a cloud, for example, and like what does that really mean? You know, like there are very many different parts of, you know, how complicated it can get. And I think that's what's kind of the beauty of just understanding and kind of appreciating what it is. Because at the end of the day, like, yeah, like as you said, I mean, it's a naturally occurring effect. It'll happen. And the beautiful thing about astrophysics, I mean, real all physics, but mainly in this thing, like that, it's kind of a thing that takes place regardless of us being there. Like the human race has played like a microscope, you know, like it's a microscopic thing in the age of the universe. And no matter where we are, if we are alive or if we're dead, like the universe will exist. The physics of that will continue existing. And like, it's just so beautiful to think about that they have such large, you know, just, what am I trying to say? Like, you know, like, I'm just trying to say, like, they have very unimaginable sizes, unimaginable quantities of things that at the end of the day, the only thing you can do with it is put it on paper and try to understand it. Because it's happening there whether or not you see it. But if you want to understand it, the only way to really do that is do it on paper because of the real vastness of what we're really studying, right?
So I think today we're going to talk mostly about like equations of state and also energy inside of stars, and maybe a little bit on how gas clouds collapse. But before we get into more of the details of that, we'll just continue along this story that astrophysics courses are trying to tell. So after you're able to describe kind of these like large scale collections of particles in space, you talk about, well, what happens when, you know, you let gravity take over, and you talk about the interactions between gravity and pressure, and how sometimes if you have a really big gas cloud, gravity is going to contract it. But then if you've seen a little bit about the physics of gases, you know that if you have some type of volume and some type of temperature and the gas compresses, the pressure is going to go up, which is actually going to cause, you know, the particles to move outwards. And so then there's this kind of interplay between gravity and pressure. And when does the gas actually turn into a star? What does it mean for a gas to turn into a star? Right? Actually, I think the definition is that nuclear fusion occurs. As soon as nuclear fusion occurs, then it's a star.
Doesn't nuclear fusion also occur in a protostar, or am I wrong?
I don't think so.
No.
Because when nuclear fusion starts, that's when you like hop onto the main sequence. If that doesn't happen, then you're just kind of like, there's like convection going on and just like energy transport within the gas.
Mm-hmm.
But like there's nothing really, nothing's alive, essentially.
I guess, yeah, nuclear fusion kind of starts the whole process.
Mm-hmm.
Have we spoken about like nuclear fusion
I
at
think
all
we have.
in depth?
I think we have. We can get back to it though, because we're actually on this step of like in our course right now, we're learning about nuclear fusion and pre-main sequence. So what it takes for gases, and how do you describe gases that have yet to become stars but are about to. And then after you talk about making a star, you get to the main sequence. And the main sequence is the longest stage that a star remains in. How do we know this? Well, you can do a little bit of mathematics about how long it takes to burn hydrogen if a star is made of mostly hydrogen versus how long it takes to burn helium and all those other elements. Or you can look into the sky and see that most of the stars in the sky are on the main sequence. Therefore, they probably are there for a very long time. We have evidence either way. After that, after you're on the main sequence, what happens when you run out of hydrogen? Well, if you have enough mass, you have enough gravity pushing into the core, you could fuse other elements, and you could start veering off of the main sequence, but continuing on into the red giant phase, the red giant branch. Or if you don't have enough fuel, I guess, to keep burning, then you turn into something like a degenerate remnant star, which could be either a white dwarf or a neutron star, which we might talk about today.
Degeneracy is kind of,
actually, yeah, we will talk about that.
We will talk about that. It kind of goes with
sure.
equation of state,
Yeah.
and like talking about like different levels. But and what's interesting about all of this is that these gases, first of all, can also make the star. Like before we actually even go into the fusion of it and talk about the actual making of the star, this gas can also have very many different properties. Right? Like the gas can either be kind of like a classical gas and kind of idealistic, and like in physics, well, we call that an ideal gas. Now there are specifics, or there are properties that an ideal gas needs to solve, but usually when we're talking about gases in like clouds, we can make a safe assumption that most of them are ideal, especially like before the whole phase of them actually going nuclear and going into the protostar and then the actual stellar phase. We can definitely assume, or at least like to a brief extent, that they are ideal.
It's not really a safe assumption, but I think it's just more for convenience.
Yeah, I don't think it's not actually an ideal gas, because there's no perfectly ideal gas in the way. I should be knowing this, but what's like the definition? Not the mean spacing definition, but like the other definitions. Like it has to have some temperature. Like there are certain points that kind of a gas needs to kind of like check off to be ideal. But like the biggest part of the gas being ideal is very simple. So in quantum mechanics, there's a thing called the de Broglie wavelength. Now I know I'm mispronouncing that, but I think that's the English pronunciation. So the de Broglie wavelength is every object has a de Broglie wavelength. And what's the best way to explain a de Broglie wavelength? It's basically like your quantum mechanical wavelength, right? And every gas, therefore, also in space, would also have a de Broglie wavelength.
The particles of the gas.
The particles of the gas. Exactly. Now, the particles of the gas are also, not obviously stuck together, because they are a gas at the end of the day. So there is quite a large intermolecular spacing between them. So the question of, is it ideal, or is it or do we treat it a little quantum mechanically, is this spacing between these particles, like the average spacing, it's called the mean spacing. So is the mean spacing between these particles greater or less than the de Broglie wavelength of these particles, of this gas, of the particles in the gas? So if the mean spacing is much greater than the de Broglie wavelength, which is usually the case when we're dealing with, these stars, or at least gases before they turn into them, we can assume it's ideal. But the moment that's no longer the case, and this can happen when the density rises, if they're really high dense regions of space, then we start treating it a little bit differently, and we get a little more into quantum mechanics, and the gas is now described via, I don't know if it's described via Fermi, like fermions. It's kind of like what's the word that I'm exactly looking for? I'm forgetting the exact word that I'm looking for. But
Fermi statistics? Is that
no, Fermi. It's not Fermi statistics because it's like the type of distribution that they follow. Oh, okay. It's just the application itself. So the ideal gas that we have follows the Maxwell distribution, and that's kind of basically stating the number of gas particles. Like if you want to find like the number density of gas particles in this cloud, what is the distribution? Right? So the Maxwell distribution is kind of also called the speed distribution. So it kind of basically is simply it's not normal. What is the exact word for it? Or do we just call it
I think it's like the shape of it is the Maxwell.
It's Bell, but do we just call it?
It's not a bell.
It's not a bell.
No,
it's not a bell. I'm mistaken then.
It looks more like a. Is it like a Rayleigh distribution? Do you know about that?
Yeah, no, I think
it looks more like that, but I don't think like mathematically it's the same.
Rayleigh is more tail heavy, right? Like right skewed.
It is, yeah.
Is that Maxwell? I think
course,
Maxwell's out. Yeah, no, because RMS. Yeah, no. Maxwell are kind of right skewed distributions, and again, they're basically just representing like the velocity, like the distribution of the velocities of the different particles. And again, because it's kind of written in classical mechanics, it's treated in one way, which is Maxwell-Boltzmann statistics. Now, in the other situation, when we have the Fermi, it's not called Fermi, that's something else. Fermi is something else, like Fermi energy, that's something else. But it kind of goes into like a fermionic state of gas. Like maybe that's a better word to say, because at the end of the day, all these gases are basically fermions, but we're not treating them like that. Because at this level, when this mean spacing is less than the de Broglie wavelength, we have the Fermi base or the fermions basically dictating with Pauli exclusion principle. So we have these particles that are now coming really, really, really close to each other that are now being kind of repelled, not because of general forces, but simply because of quantum mechanical facts, which is the Pauli exclusion principle. And this just is a kind of a consequence of when we have our gas either too dense or basically it's no longer ideal. And a lot of cases where we deal with non-ideal gases is where we use I don't really know what it's called. I'm going to call it fermionic gas. I think that's a word for it, but let's call it a fermionic gas. And it kind of represents a little more quantum mechanical state of the gas. So this is kind of just like a preamble to before we really get into the nuclear fusion of it all and really get into the star of it all. Because when we get there, then it's no longer, well, it can still be described this way, but then we're kind of looking more at the star and a little more at the fusion, how its, energy is really working rather than mainly focusing on the gas.
Mm-hmm. Well, I was going to finish the whole tract of the course, but I guess you've gone on this tangent. I'll just say what I wanted to say.
I simply explained the gas that I think, we learned this before.
Yeah, I know. But I was just going. Fusion. It's fine. I'm just saying that I was saving something for later, but I'll just say it now because you've already said all this. But basically, what happens when your gas is very, very dense and you can no longer treat it as an ideal gas? Mm-hmm. Obviously, denser materials or denser gases have higher pressures. But eventually, what happens if you just squeeze a gas so tight? What happens? Do the atoms just kind of collect together and it becomes a solid? Kind of. Let me be more specific. There is a level at which specifically in a star, where the pressure being produced, like the radiation pressure and the gas pressure, is just not enough to hold the gravity back. When you stop burning hydrogen, your main source of energy within the core of your star, when that gets depleted, you no longer have this like supporting pressure, and so you just kind of collapse onto itself. And usually, if your star is not super massive, if it's massive enough and the gravity is strong enough, then you can go into, like, you can literally explode, supernova, or go directly into a black hole, or become a neutron star and then a black hole. But usually when you have like a average size / like small star, you just become a white dwarf. And white dwarfs are supported by something called electron degeneracy pressure, which is very, very interesting. And it's actually something that we talked about very recently. Electron degeneracy pressure, it's kind of this fake pressure. It's not a real pressure per se, but it acts like a pressure, and so we call it electron degeneracy pressure. But what is it? This is so interesting. So it's fermions, right? An electron is a fermion.
Oh, well, yes.
It's a fermion.
You're making me forget. Leptons and fermions are not the same, so no.
So what is an electron?
What am I saying?
Boson.
Yes. No. Yes, you're right.
Bosons
Leptons and
is the
quarks. I'm
photons,
so sorry.
yeah.
No. My brain glitched. There are fermions and bosons. Fermions consist of quarks and leptons. So an electron is a fermion because it supports Pauli
bosons
exclusion.
is photons.
No, it has
right?
to, because Pauli exclusion. This is the whole reason you're giving. Yeah.
Okay.
It has to.
So we have electrons that are fermions.
Yes.
And Wolfgang Pauli, a very smart guy, by the way, he actually comes up in the book, the Quantum book by Manjit Kumar. And
I think a lot of physicists come up in that book.
No, a lot do, but I remember him talking about Wolfgang Pauli because he was actually like very smart. He was a very smart student, and he was he was on the scene at the time.
He was on the scene.
He dropped a banger. He dropped the Pauli exclusion principle
is a banger.
So what does the Pauli exclusion principle say? Well, essentially, two fermions cannot occupy the same quantum state. Okay. And by quantum state, we mean, here's an example, right? If you have this gas at a temperature of 0 Kelvin, essentially there's not a lot of kinetic energy, right? Because in a gas, the average kinetic energy per particle depends on the temperature. And so if you have 0 temperature, let's just assume there's no kinetic energy, even though this is not actually true, and I'm about to explain why it's not true. You can kind of picture just these like still particles coming together very, very closely. So the quantum state of a particle will be dependent on its position and its spin, because we're talking about electrons. So you can't exactly have two electrons sitting on top of each other with the same spin. That would not be allowed. But what happens is that if in a star, in a white dwarf, the pressure is so immense that it's forcing these electrons to get really, really close together. But this is just a consequence of nature, the Pauli exclusion principle. It's not really something that, or I guess I'm just not smart enough to know why or to come up with an explanation.
For what?
For why the Pauli exclusion principle is a thing.
Oh, this is chemistry. This
is
electron orbitals.
Okay, but like, why though? Like, you know what I mean? Like why is it a fact of nature that the Pauli exclusion principle works? Like, we could just live in a universe that.
My best understanding is that every like this is what do you call it? Oh my god, this is grade 12 chemistry coming back to me right now, because grade 12 chemistry, we literally had a chapter on Pauli exclusion principle and describing why it works, and the whole reason was basically because I'm thinking of like the state that an electron can basically fall into. It's like the SPD. What's that called? Electron configurations. Electron
Orbitals.
configuration. No, orbitals, but I'm talking about the configuration of atoms.
Okay.
So the way that any atom or any body works is that when electrons are attracted to it or get onto it or are starting to orbit it, they fall under certain energy levels, right? They fall into S, P, D. I don't know if you remember these from chemistry.
I actually did this in 356.
Oh, interesting. Well, no. So these are electron configurations. So these are energy levels. The higher the higher the energy level, the faster the electron is moving. And a basic fundamental fact about any one of these energy levels is that it can take 2 electrons, each of opposite spin. And the idea is that only these 2 electrons can fit into any one of these states at any given moment in time. So the problem, when there is so much pressure applied by gravity that these other electrons are trying to fill it up, it is simply a fact about electrons taking up energy, just quantum mechanical fact about electrons taking up energy, that they just cannot fit into the same energy bracket because it's all taken up. So the only thing to do is to gain more, is to go to the higher energy bracket and move faster. And basically the whole pressure of it, the electron pressure of it, comes because of this velocity differential that then kind of creates a pressure gradient towards, or not towards, but that kind of creates a pressure gradient because of these differently moving electrons. So it's all mainly because of a very fundamental fact that these things just cannot be in the same, well, quantum state is just a fancy way of saying it, but like no 2 electrons can be in the same energy level is kind of like it's kind of like the idea.
So like my question was a little bit more philosophical than that.
I think it was, but I was just trying to apply like the most chemistry,
because like even what you said, it doesn't. Like
It doesn't.
Can answer why that is a thing.
You're right.
You know what I mean?
It doesn't really explain why 2 electrons, why more than 2.
Like
there probably is a reason.
Yeah, there definitely is a reason.
We just don't know.
What I was trying to get at is that this like pressure, this electron degeneracy pressure, is just kind of a property that we can observe, and it's just something that we observe, and it arises just like the fact that I'm looking out of my eyes right now. You know, it's just, I don't know why, it just happens. What was I gonna get at? Oh yeah, I was gonna get at the fact that back to this 0 Kelvin gas. You have these electrons that, because of the temperature, this like heat sink that these electrons live in, they are trying to reach the lowest possible energy state. And because of the Pauli exclusion principle, only, a certain amount of them can be in the lowest state, and then automatically some of them have to be in the first excited, second excited state, and so on. And so even at 0 Kelvin, you do still have motion, even though classically you wouldn't have anything moving at that temperature. When it comes to white dwarfs, what does this mean? This means that theoretically, the amount of material condensed in the amount of space that we observe white dwarfs to occupy should not be allowed. It should literally collapse in further onto itself, but we still see that they are a thing. And so obviously we ask questions. And well, the explanation that we came up with is, oh yeah, the material itself cannot condense further. And so we have this artificial pressure that arises that holds up the entire star. So yeah, I kind of think of it as like a glitch in reality, where it's like when you go to the edge of the map and you just like get stuck at the edge. That's kind of what gravity's doing, right? It's contracting, but then it gets to the edge of the map and it just stops there. Like
there's a level,
and then people are like, wait, why is this happening? It's like, well, it's just like fundamentally the particles just cannot go further, so it just stops there, and then you have white dwarfs. However, there are more dramatic.
Yeah, I was just gonna say.
There are more
We
dramatic.
can compress it further.
We can.
What will happen though is the question.
We will get to that later.
Oh, I thought we were
Because
getting to
I just wanted
Okay.
to finish. I really wanted to finish this
No, go
whole
for it,
like
go for it.
this whole
No, but like
storyline.
we're so we could okay, go for
I
it.
know,
Go for
but
it.
this is really quick because it's really interesting. So I was talking about post-main sequence stars. You got degenerate stars. We study the stars. What kind of stars are out there? What do they do in their lifetimes? How do they die? How do they get born again? But then there are bigger questions to ask. For example, how big is the universe? How do you even go about calculating these things? How old is the universe? How does anybody know how old the universe is? These are all questions that we want to ask. Now, one thing that if you're interested in astrophysics, you should do is search up the distance ladder. Because
Oh,
this
isn't that my presentation?
is it?
I think so.
It is your
I think
presentation.
that's my presentation.
So
oh shoot.
the distance.
I don't actually know about this yet.
Yeah,
I
well,
still have to study on it.
this is what the distance ladder is. It's just like a scale of distances, and the tools that we use to observe objects at each of these
Are
distances.
these standard candles, like that kind of stuff?
That is one tool that we use
Oh,
at
shoot,
a
that's
certain
cool.
distance.
That's
Now,
cool.
I don't have like the distance ladder memorized, but I do know all like pretty much most of the tools that we use. Like for example, on very close scales, we use stellar parallax. For example, or not for example, I guess by definition, when the Earth goes around the sun, it actually has like a difference in position of 2 astronomical units, which is actually very far. It's around 16 light minutes. This change in perspective can actually change the position of stars in the sky. It's like when you look at something and you close one eye and then you open and close the other eye, and how that object changes position in your view because your eyes aren't at the same place. Well, what you can actually do using a little bit of trigonometry and a little bit of mathematics, you can find out how the angle that it changes on the sky relates to how far it is. However, if something is very extremely far, you might notice that if you look at, a tree 100 meters away from you, if you open one eye and close the other and then switch, it's not going to move at all because it's just too far. And so this is where we have to look at other techniques, where we look at the first rung of the ladder, where it's like, okay, we can use stellar parallax to tell how far objects are. But now when the objects stop moving in the sky after 6 months of the Earth going around the sun, we have to go on the next rung and use different techniques. Like, for example, something that's very powerful is a Cepheid variable star, where we found out that these stars that are pulsating, the pulsation rate of the star is related to the brightness of the star, the intrinsic brightness of the star, which means that if you look in the sky, you see a star pulsating, you're like, oh, that's a Cepheid variable. Now, you see it pulsate at a certain rate and you say, this should have a brightness of 1 unit. However, in your telescope, you only see a brightness of 0.3 units. Well, turns out the further away things are, the less bright they are to your eyes. For example, if someone's on the moon and they hold a flashlight towards the Earth, you're probably not going to see that light, but if you hold it right in front of your face, it's going to be really bright. So it's just, the factor by which a star dims is related to the distance. There are also other factors. For example, if there's a ginormous cloud of gas in between us and the star, the gas is going to absorb some of the light and the star's going to look dimmer. But that's something we'll just not worry about for now. So you can tell.
What is that called again? That's called
absorption.
No. It was called something like we literally found like of gas like and then we had to like measure the amount. I mean, opacity is kind of.
No, I think it's like.
But it's not really opacity.
I think it's called absorption, to be honest.
What's it called?
Like the absorption constant, I remember it was lambda.
Wasn't it? I mean, this wasn't 2-2. This was second year.
Yeah, second year.
When we when it was kind
It's
of
like dust absorption or something.
Yeah, yeah, yeah. That's what
There's
I'm
a word for it.
Yeah,
I
no, there's a
kinda
word.
forget.
There's a word for dust. Yeah, no, dust. Okay, continue on your story then. I'll think about it.
But yeah. So now we'll not worry about the dust. We just
Yeah,
worry
just-
about how if something is very far, it looks less bright. You can do a little bit of math once again to figure out, okay, if something looks this much dimmer, then it's this far away compared to what we know how bright it should be. Now, the period of pulsation is directly related to how bright it should be. So you just do the little comparison and you're like, this is how far away that thing is. So now, using Cepheid variables, you can tell how far things are just by the properties of the star itself. And you don't have to deal with actual like motion and what we did for stellar parallax. There are other things. For example, if you want to look very far into the past, you can look at the redshift of something. You can point a telescope at it and you can see the stellar, not the stellar, I guess it could be a galaxy. You can see the spectrum of electromagnetic radiation that it gives off. And it turns out that, okay, the wavelengths are stretched out a lot more than what they should be. And so accounting for that stretchedness, you can tell exactly how far it should be. And now at these scales, distance is also related to time. So if you're looking at like a really old quasar that has a redshift of like, what was the redshift? Like the highest redshift quasar, I'm pretty sure I did a presentation on this last year. It was like a redshift of like 7, which means that it was, you could calculate it, but I think it was like born in the first like billion years of the universe. So very, very old, very far away. And then you can look at something like the cosmic microwave background radiation, which has a redshift of, I don't know how much, but
We're not
it's
really. You
it's
can't
the
really measure that.
it's
with
the
them.
it's the last thing. Yeah, you can. Of
Not
course
with
you
a
can.
telescope.
Of course you can.
I mean, like you're not really.
it's radio waves. It's
Yeah,
been
but
stretched out by that much. You can tell the
if you're-
redshift.
I guess so, I guess
1,000%.
But it would be
It's
such a
elect-
faint. It would be such a
it's a-
faint signal. Like the signal you receive would be. I mean, like, what do you mean? It's like static. Literally, like the static you receive
That's
is like
what you need.
part
All you need is a
background
signal.
radiation. Yeah.
All you
okay.
need is. You think people haven't calculated this before?
No, what? Of course, of
Why-
course.
why
I'm
you-
not.
why
I'm
you
just
think
saying
it's
you can't like do
impossible?
it. Like it's hard to like just look at it.
I-
Like I'm saying, you're saying
What
look
do you-
at a redshifted star, you can see it. Or look at the CMB.
What do you think they did to calculate? They looked at it. That's what they did. That's
Well,
literally
I'm
what they.
intrigued.
Do you think the people who calculated the redshift of the CMB were any different than you and I? No, they just had a telescope and they looked at it. They're just people who did it, and they did it. So they looked at the CMB, which is actually the last thing that you can see, because the cosmic microwave background radiation is actually at the time of recombination, which is when photons were allowed to travel. Before that,
It's
was
basically
just,
the very first radiation from these photons.
Yeah. I guess
kinda being
travel wasn't
absorbed.
the right
Yeah, no,
word.
it's kind of being like absorbed because in the very first moments of recombination, when these particles were recombining, there were a lot of photons that were being absorbed and released and absorbed and released. And the theory is that the CMB is basically a culmination of all of these photons. And it's been traveling. I mean, it'll travel forever until the last photon. I mean,
well, no, it's because the universe was expanding at the time, and because
no, but I'm saying, what is the CMB?
Yeah,
It's
but-
just
but
because
it's-
the absorbed and
it's because
emitted
before it
photons.
was super dense, photons would just be emitted and absorbed
Exactly.
basically immediately. So you can't really see anything. Like if you were alive back then, you were to just pop up. No, I'm saying if
I
you,
mean, okay.
if you
sure.
were an observer back then,
Sure.
you wouldn't be able to see anywhere in front of you because all of the photons that would enter your eyes were emitted right in front of your eyes. So you would just see this opaque glow, and apparently it was orange, right? Wasn't that the PBS Spacetime video? He said if you were alive back then, the whole universe was orange because that was the wavelength of the light, something like that. Something like that. But yeah, so anyways, recombination is when photons had enough room to actually escape and just travel in a straight line for a really long time. And then the photons that have been traveling ever since that very moment will now be entering your detector and you detect it and you say, wow, that photon has been traveling for a really long time, exactly like 13.3 billion. Sorry,
It's
not
so
billion.
uncertain too, though.
It's very uncertain, but it's been traveling for at least, we can say 13 billion.
Sure.
We can say that much.
Sure. Sure.
And, you know, based on how space-time stretches wavelengths, you can tell that, oh, I'm getting a radio wave, but it should actually be a much higher energy form of electromagnetic radiation. So the difference between those two is related to how old it is. So that's how old we can tell the CMB is and when the universe became transparent.
I don't know what this had to do with our story, though.
Oh, no, this...
Talking about stars, we're on neutron
This
electron
had to do with
pressure.
with the distance ladder.
Okay, because I kind of want to talk about. Okay, so a little backtracking. I'm back on the
actually,
story.
Last thing.
Go for it.
So we talked about stars in the beginning of the course, and we talked about cosmology, the distance ladder. We just asked pretty much the big questions in cosmology. Like, we talk about galaxies, we talk about how old it is, how big the universe is. We talk about how it began, the Big Bang, the first few like micro, doubled femtoseconds of what happened in the Big Bang. And then we can ask like philosophical questions like what happened before the Big Bang. We also talk about the shape of the universe. You might think in your head that it's like a sphere that's going in all directions, but you don't really know.
I mean, on a macro level, it's basically flat.
See, that's something we do study. What does it mean for the universe to be flat?
No,
right?
there is.
But what is that?
Yeah, there's a whole thing. I'm not very well versed in it,
Yeah.
but I'm not very well versed in it. But like I know because just by monitoring the CMB, you can see that the universe is relatively isothermal, and that kind of leads you to, okay, if it's isothermal, there are, it's a relatively uniform density. So I mean, there's some reason from there. I don't know where the flatness comes from, but I don't think like that's why you can't really experience it as like a sphere.
I think.
But I don't know. I don't really know if there's a real.
Beyond that, we talk about, is the universe expanding? Is it static? Does it have curvature? Like on the macroscopic scale, is it negatively curved, positively curved, not curved at all? Things like that. But yeah, that's pretty much the whole story.
And also a cool thing, I don't know if we mentioned this before, but the age of the universe is a super simple calculation. So there's a constant called...
Very rough.
I mean, very rough.
That calculation is very rough.
I mean, it's experimental. It's super experimental because it's based off of the Hubble constant, which is it's purely an experimental constant. It just so happens that, okay, when you line up these stars and you line up how fast they're moving away from us...
More than stars.
When you line up any object in the universe with how it's kilometers per second, so speed versus their distance. So it's kilometers per second per megaparsec, and if you do the math, the dimensions are basically just 1/2. So if you flip it, hypothetically, you basically should get the age of the universe. And
but actually, you skipped a lot of details.
No, of course. No, but I'm saying the general idea of the Hubble constant is that, hey, when you plot these velocity versus distance, you basically see a straight linear line.
But okay.
Against anything. And you can actually see every single, observation that's made. If you put it on the Hubble diagram, you'll see a relatively linear thing.
But also, you're talking about graphs and plotting things, but like, what are you actually talking about? So what Rehan just explained is that if you measure a star, you can measure based on the redshift how fast is it moving away from you, and then based on that you can use the distance ladder, use like other methods to find out how far it is from you. Well, so it turns out, okay, if you're this far away from us, you move away at this speed, and then if you're even further away from us, you move away at an even faster speed. So then what we do is we look further and further out into space, and we see that the redshift is higher, which means you're moving away faster. And so if you were to plot your radial velocity away from us based on how far you are, you get this linear relationship where it's like, okay, if I'm this far away from us, then I have to be moving away this fast. And this is not a property of the object itself, it's a property of space-time expanding in between these two objects. And so if you imagine space-time being in one single spot in the universe and then expanding from there, if you were to begin at that point and then expand out to the edge of the universe, and we could pinpoint the edge of the universe, what we do is we would just place that on our graph where it's like, oh, you're this far, so you should be moving away this quickly, right? We can go all the way to the edge of the universe based on our model. You know, we just extend our linear relationship all the way to the edge of the universe. Well, it's like, okay, I have a relationship that tells us 1/seconds, right? The constant is 1/seconds. And so if I want to backtrack from the edge of the universe all the way to the beginning, I can just take this like frequency. It's not really a frequency, but you know, this 1/seconds frequency and invert it, and I get the period, which in this case, the period is just from the beginning to the present.
That's the idea.
And it's not actually like a period. It has nothing to do with oscillation, but
You're just making a comparison between 1/seconds and seconds.
Yeah.
Exactly. Now, see, unfortunately, because of how you started, how are we going to take this back to stars? Like, there's so much more to talk about.
We don't have to.
No, I want to though, because we didn't finish electron
listen.
degeneracy.
This is our podcast,
Okay.
our rules. You can go to stars if you want to.
Then let me say this, because I do not think we finished with that at all, and I think we should give it a little more justice, because we were kind of talking about these extreme scenarios of these stars and this degeneracy scenario and what really happens, you know, when stars kind of go a little haywire, you know, when it's a little more pressure than it should be, a little denser than it should be, and, you know, things that shouldn't happen are happening. So, like, I mean, it's an interesting thing, and that's actually what we're exploring right now, because a lot of these pressures, a lot of these ideas are stemming from very powerful foundations, which we are learning, and that's kind of the main idea behind understanding what's the difference, right? So white dwarfs, we understand, is supported by electron degeneracy pressure. And as I said, basically what's happening is that electrons are moving faster and faster and faster as you go up. And you have, because they have more energy, they're going on these higher energy levels. So there comes a point, right, as we were saying, like, what if we're continuing to pressure it? To apply pressure to it. Let's say we continuously add more mass, keep the volume the same, so we're increasing the density. And we're same volume, we're just increasing the density. What happens is quite interesting, because now the electrons also have this insane force that's acting on them, such that the highest speeds is almost near the speed of light. So at the point where the highest speed of this electron is the speed of light, is what is called the Chandrasekhar limit. So this is kind of the maximum limit for any white dwarf to basically exist, because any higher than this, and there's way too much pressure. I mean, there's way too much gravitational pressure for the electron degeneracy to hold up.
I actually didn't know where you were going with that, and that was a really good explanation.
Thank you. Yeah. So that's the idea behind what happens at this limit. And what goes further is even more interesting, because when these electrons, because remember, electron degeneracy pressure, the star is not only made of electrons, remember that. It's also made of protons, right? It just happens to be in the nucleus. So what's happening is when there's so much pressure that is applied onto this star that the electrons, they're not being forced from their energy levels, but they are being forced into the nucleus. That is an interesting phenomenon, because again, this only happens. Remember, Pauli exclusion is not violated. Still, everything is good. They're still in their energy levels. It's just that those energy levels are coming closer to the nucleus because of the amount of pressure that you're applying onto it, because of the more electrons that you're applying. Remember, as I said, when you're increasing the density, you're basically increasing that higher speed. So you're making those energy levels, higher and higher and higher until you reach some maximum. So when there's so much pressure that these energy levels are basically kind of squished into the nucleus, something very interesting happens with the quarks. So as we know, electrons, protons, neutrons are all made up of quarks. And it happens that when you combine a proton and an electron, you make a neutron. So what happens in these very heavily pressurized environments is that the electron degeneracy pressure actually converts to neutron degeneracy pressure.
Is that actually what happens?
Yeah. Because
didn't know that.
over 80 to 90% of the star is then completely neutral. Now you might be wondering neutron, because remember, it's not fully neutral because neutron stars
still
have
makes a
very
huge-
heavy
yeah.
magnetic fields, so it can't be neutral, but most of them are. And it's simply by the by the fusion of these particles.
I didn't know that's how neutrons were made.
Interestingly
didn't know
enough,
that.
right? And this basically causes, again, another degeneracy pressure because same rules apply, right? No two things can take the same state. But this time, it's one neutron per quantum state instead of the two electron flips.
Because now there's no spin, right?
Exactly, because it's neutral. So this means it's a lot tight. Actually, I don't know why it means it's a lot tighter, but it does mean that it's a lot tighter because it can go to very much higher densities. That's why neutron stars are so dense. You know, like a teaspoon of a neutron star is the mass of the Mount Everest. Exactly. So like that very nice comparison because it's as small as Manhattan, as heavy as teaspoon as heavy as Mount Everest. So the idea behind it is all supported simply by this other. So it's the same fact that supported electron degeneracy, just a little bit tighter. And obviously, as you can see where this is going, let's put some more pressure onto it. Let's put some
keep
more
going.
pressure onto it.
What's the limit, though? What determines the limit between a neutron star and a black hole?
This is known, I have it actually right here, the Tolman-Oppenheimer-Volkov limit.
Wow.
Yes. So this is about 3 solar masses. And at
Really?
this limit, wait, was it? If the mass of a neutron star reaches 3 solar masses,
Wow.
the speed of the neutron, again, reaches the speed of light. So the top neutron speeds.
Oh, wow.
Because again, it's always the speed differential. The speed differential is causing
Right,
everything.
so like the Chandrasekhar limit is like the same. Like,
It's the same.
wow,
It's just that
okay.
exactly. It's the same. It's just the version of neutron stars. Now, hypothetically, and I was reading this and I don't know enough about it, so I'm not going to go into it, but I will just say the word. So if you want, you can search it up. But hypothetically, a neutron star, when it reaches this limit, should turn into a quark star. Now, I don't know what that is. But it sounds cool. And if you want to search it up, you can.
Oh, I know what that is. It's where
It's
basically,
hypothetical, though. It has not been found yet.
it's basically the inside of the neutron star becomes so packed.
Okay, that's even more.
to such a crazy level that essentially the boundary between like neutrons just evaporates and you're just left with this plasma of quarks.
That's
And it's
actually
just like
called
a-
quark gluon plasma. Is that
so
the
it's
quark
just,
star?
it just becomes like a soup of quarks. That
So
just,
that's actually called quark gluon plasma, and that is currently a kind of like a state of matter.
we don't know
that's-
that for sure though.
No,
that's
no.
the thing.
Okay, yeah, no,
Or well,
yeah.
we do. We know it.
We know what quark gluon plasma is, but we don't know that actually happens.
Yeah.
Well, we know that hypothetically it
Yeah,
should.
yeah.
We just we have not observed it. So what happens in reality is that it turns itself into a black hole. And this is because I'm assuming of the excess mass. I think the quark star is maybe the reason we don't see it. Again, I'm completely inexperienced in this and I'm just completely talking out of my head, but maybe it's something to do with like it has to be like a certain range of mass, and if it's over that it turns into a black hole. And usually when a neutron star becomes a black hole, it absorbs too much anyway, so it turns into a black hole. Maybe something like that, I don't know. But yeah, so then the last final stage is a black hole, which we've already had enough episodes on. But that's basically kind of like just the stage of what's actually happening in these stars in a little more detail. Again, because as I said in the very beginning of this episode, I think we've covered a lot of these general topics before in the astronomy episode, but we've never gone into this much detail. And that's just going to be each one. It's just going to be more and more detail because that's how we're learning it, right? And I mean, that's hopefully your goal too, right? Just to learn more about the same material. Because you just want to know more and more.
I think the next astronomy episode we do will have to be more like in-depth main sequence.
And you want to do that with a professor, though?
We could, yeah.
We could.
100%.
We could.
Yeah.
I mean, we could do it after this semester, after we finish this particular thing, or we could also do it next semester.
Yeah.
Anything else we want to talk about? I think That was a nice rundown of like a little bit of stars and what we're learning.
Oh,
a
we
little
can
bit of
actually talk
gases.
about one last thing.
Go for it.
We can talk about the free fall timescale.
Okay.
That's a cool one.
Okay,
That's
this is a little more on gases now.
Yeah,
so
we
we're
should have done this more in the
going,
beginning.
yeah, but you know, it is what it is.
Whatever. So here we go. Time scales. Time is very cool because you know,
Nice way to start it.
we live in time. Um, so we want to know how gas clouds collapse, fall on each other, right? So one thing that you could ask is, how long does it take for a gas cloud to collapse, right? One way to answer this question would be to go to brilliant.org and to check out their course on astrophysics. Rehan and I were actually checking out this course before recording this episode, and wow, is it detailed, and wow, do they have amazing topics, everything that we've spoken about and more. Oh my god, we even on one of the astronomy episodes that we recorded in the past, we talked about how humans in the past were calculating the distance of the moon from the earth, or the distance of the sun and the mass of the sun. How did they do
Radius of the earth, size of the earth, all
Brilliant
that kind of stuff.
actually has one of the very first courses in the section where they talk about distances, where they actually have an entire course on stellar parallax that we talked about today, also standard candles, apparent magnitudes, all these things. They have a course called Greek estimates where they teach you how the Greeks measured distances and sizes back in the day. Oh my god.
That's
where
actually a really
you
cool
couldn't
course.
just Google the answer. You had to go into nature and figure it out for yourself.
That must have been a good time.
So interesting. They have everything over at Brilliant. Life cycles of stars, cosmology, dark matter. Yeah.
Super simple. All you need to do, if you want to go check it out, you can go in the link in the description below, or simply type brilliant.org/MPP for a 20% discount on your premium subscription, or, you know, just click it and just check out the website and see what you like.
Boom.
That's basically it. Yep.
Now, timescales.
Timescales.
So there are very various ways to estimate timescales. How does a gas cloud collapse in on itself? Okay. Now, one
Or,
way.
well, that's one time scale. Like,
What?
I mean, okay, sure.
Right,
sure.
the free fall time
Yeah,
scale is
because
one
there are many
time scale.
because time scale as well. What are you measuring?
Yeah.
In this case, okay.
So
go for it.
the free fall time scale is kind of the first time scale that you encounter. And this is the time scale. Actually, it's the smallest time scale that exists when you want to approximate something. And so what you do is you kind of forget all of the laws of physics except for gravity. And you say, I have a gas cloud that has this much mass. Or you can say, like, it's this big and the density is this much. How long will it take for the very outside edge of that cloud to reach the middle? And so what you do is you turn off pressure and you turn off intermolecular forces, all of these things, and you just observe how long will it take for this cloud of this density to fall in on itself. So you can do some cheeky mathematics, and you actually find that it's inversely proportional to the square root of the density, and it actually doesn't depend on anything else. How interesting. Okay. And this is actually, this was one of our like problem set questions, which we can talk about because the solutions are out. No, we're not going to go into detail, but still. So one of our problem sets dealt with, so you're inside of the earth, and what you do is you throw a ball. And like, imagine there's a tunnel in the earth that goes from one side to the other, and you throw a ball very far, right? And so eventually that ball will go up, but then the force of gravity will pull back down onto that ball, and you know, it will come back through the middle, down the other way, and then it'll oscillate up and down if you have this like magical tunnel, right? It turns out that the period of oscillation is 1/4 of the free fall time scale. why is that? Well, you can kind of imagine if you were to like adjust where you were in time in this oscillation, you can imagine when the ball is at the peak of its trajectory and it's instantaneously not moving, you can imagine as if that ball is a particle of gas in a cloud, and you turn on time and you turn on gravity, and suddenly the effect of gravity starts to pull that ball closer and closer into the earth until it reaches the middle. That actually, like that section, that interval of the oscillation is 1/4, because the whole oscillation would be, from peak to middle to bottom, back to middle, back to the peak. That would be one full oscillation. And so if you just take from the peak to the middle, then that's 1/4 of it. And we did a little bit of math for our problem set, and we actually found that 1/4 of this entire period is the free fall time scale. Very cool.
That was a really cool lesson that we kind of learned from there. Man, these problem sets that we're doing, super cool. I mean, we don't have to get into that, but that's definitely super cool.
There are other time scales though. I can just briefly mention, unless you had one.
I mean,
mind.
there's one that I was just reading on that's really cool that we know about, but we haven't learned in class that I want to talk about, and this is actually much shorter than the free fall time scale, and this is called the collision time scale. How often, on average, do you see collisions? So this is
see, because I was just saying, I said that the free fall time scale was the shortest time scale, but this is for like collapsing. This like the
no, I'm just talking
collision
about particles
is not,
in a gas.
Yeah, it's not about collapsing.
No, absolutely not. No. This has nothing to do with the collapse of the star. Or the cloud. This is simply because remember, time scales can really be anything.
Right.
When it's just a scale of time. So you're just saying, okay, when you're measuring these things, this is the magnitude of time that you're looking at. When you're measuring this is the magnitude of time you're looking at.
I wanted to like compare to a different time scale
for
you want collapsing
to do that first?
stars. But you can
okay, I mean, it's just very brief because it's something called, I think that we've discussed before. Have we discussed the mean free path here before?
No. I don't know.
I mean,
this
the
must
mean
have been
free
a very
path.
long time ago.
Okay, it's basically, just theoretically, I'm not going to theoretically, the mean free path is the average distance that a particle will travel until it hits another particle. So if you have a bunch of particles in a gas, the mean free path just tells you, okay, let's say you have a mean free path of 1 centimeter. So that means basically what you're saying is on average, if let's say a particle bounces off of another one, like in another centimeter, it'll hit another one. Right? And in another one, and a centimeter, it'll hit another one. So that's the idea of the mean free path. The collision timescale is simply an idea with, okay, if you know the velocity of these particles, which is given by Maxwellian distribution or fermions, remember the name I didn't know about, or whatever type of particle it is, if you know the velocity distribution, you can kind of get a good estimate for this. So it kind of gives you a good idea about, okay, on average, how often are you expecting collisions to happen, which then gives you a good idea about, sorts of things like nuclear energy and nuclear fusion. So just like a quick reference to get some numbers in, the sun, if you shut off the pressure of the sun, the time scale, or the time that it would take for it to collapse, is around 1,600 seconds. So that's around half an hour. And the collision time scale is on the order of 10 to the negative 10 seconds.
Right, because they have nothing to do with each other.
Of course, nothing at all. But I'm just bringing it up as a reference point just to say, okay, these are the values. So just think about it, because I mean, it's nice because the sun, someone can picture the sun. Someone can picture, okay, turn the pressure. You don't really know what that means, but like turn the pressure off of that object that everyone knows and loves. What'll happen? How long will it take to disappear? That's basically it. Free fall.
Very nice. So yeah, I guess the last thing I just wanted to compare to is a different time scale for stars collapsing, and that's the Kelvin-Helmholtz time scale. We didn't talk about the virial theorem, but I guess we can keep that for next time.
We talk about the virial theorem, bro.
We'll talk about that next time.
Jesus Christ.
So yeah, the Kelvin-Helmholtz time scale, what this does is what you do is you take the energy of the star. What is the total energy of the star? So, there are some very good estimations that we have. This is a very big part of astrophysics, is learning how to just approximate how big things are, how dense they are, what the mass is, because there's no real use in finding the specifics. Just kind of an approximation is usually good enough. The same reason why we don't count the particles of gas that are in this room, and we just talk about the gas as one object, right? We approximate it as one thing. So yeah, I was talking about energy in a star. So there are good ways to approximate the total energy in a star. You can just add up the average kinetic energy per particle to the total gravitational potential energy in that star. And so, like, kind of the idea of, what is the total gravitational potential energy in that star is you would picture a particle at one point in the star, and you'd ask, what is the gravitational potential energy of that one particle? And then what you would do is you'd just integrate throughout all of those similar particles that have a similar gravitational potential energy, and then you just integrate from that point just all throughout the different radii of the star, and you get a number after that. Now, this is how much energy the star has. So, what does it mean for like the star to die? I guess this has nothing to do with the free fall timescale.
No, not really.
Not
but
really.
it has stuff to do with like stars collapsing.
I just realized that now.
Like,
so
I'm like, this doesn't really have a
nothing
relation.
to do with. Yeah, no.
But I mean, it's
It's
similar
still
because
cool,
in
yeah.
free fall you're asking
Yeah.
turn the pressure off.
Yeah.
In Kevin Helmholtz
How?
you're saying turn the nuclear fusion off.
Yeah.
So that's so
No,
it's-
actually, you're not doing that. I'll explain why.
no, what?
Yeah, you're not doing that. So the Kevin Helmholtz timescale is basically how long a star will burn for,
Yeah.
right? But this is a lot of assumptions, right? Assuming that all of the energy in the star will be burnt.
No, that's the nuclear time scale.
That's the Kevin Helmholtz.
Kevin Helmholtz is if you turn off the nuclear fusion. The nuclear time scale is how long
Oh.
it'll last.
Right.
With the purely
Yeah,
through
yeah,
nuclear
but no,
energy.
but Kevin Helmholtz is like you turn off nuclear fusion.
Yeah.
But the energy will be like radiated away
yes,
in the
yes,
same
yes,
fashion
yes.
as like.
But the time scales are different.
Yeah, no, they
The
are
time
different.
scales are different because one is the nuclear energy of the thing, one is kind of the gravitational
No,
energy
you're right, yeah.
of the thing.
But
So-
essentially, you take the total energy, and something we didn't talk about, but luminosity. Luminosity is joules per second.
Flux, isn't it? Flux. It's used
That's
to flux.
per unit area.
Oh, you're right.
Flux is luminosity per unit area. So luminosity is how much energy per second is this star losing. So you can calculate that. You can say, okay, the star has this much luminosity. What you do is you say, okay, let's take the total energy of the star and we divide it by the luminosity. So what you're doing is you're assuming that all of the energy in the star will be just radiated away via electromagnetic radiation. How long will it take for the star to stop burning? And so that's what you do. You do joules divided by joules per second. If you do a little dimensional analysis there, that gives you units of time. And so that's the Kevin Helmholtz timescale. How long can the star survive based on just the current total energy of that star?
So I think, yeah. So I have numbers of the sun here. So I think that's fun to compare. So as we saw, free fall was 1600 seconds. That's around half an hour. The Kevin Helmholtz timescale is about 10 to the 7 years. Quite a lot longer.
Quite a long time.
Quite a long time.
Yeah.
And the nuclear timescale that I kind of very, very, very briefly mentioned that we don't really have to get into, but it's basically just if you're talking about the total nuclear energy from the hydrogen burning to helium. Again, Kevin Helmholtz is gravitational. This is kind of nuclear energy. So you're asking about, okay, if all of this had to kind of radiate, so at its current luminosity, if it was radiating it away, how long would it take? And for the sun, it's around 10 to the 11 years.
And which is more accurate, right? Which is a more accurate representation, I'm pretty sure. But none of these timescales are 100% right. But I'm pretty sure the nuclear timescale is the closest
To what?
to the actual lifetime of a star.
So the sentence right under is the actual lifetime of the sun will be about a tenth of the nuclear timescale
Wow.
because its luminosity will increase greatly when it becomes a red giant.
But-
okay, I think it's also encompassing the red
Yeah,
giant.
exactly.
It's not
But
only doing the star.
A tenth of that is still closer than 10 to the 7, right? Because the 10
yeah,
to the is 10 to the 10.
10 to
So,
the 10. Yeah,
so the
exactly.
nuclear timescale is more accurate, but
Yeah.
that's not accounting for what happens to the star once it loses like this initial, I want to say layer of energy, but that doesn't really make sense. Like once it burns all of its hydrogen, you know, something different happens. The star goes through puberty, right? It changes, you know? So the nuclear timescale doesn't really take that into account.
Yeah. There are a lot of like discrepancies with these timescales. Again, there's no real like significance of them. It's just if we're dealing with, you know, a certain problem, we'll deal with a certain timescale. You know, like you're talking about particles colliding, it'll deal with a collision timescale. You're talking about nuclear fusion in a star, it'll deal with a nuclear timescale. So you're just like comparing it to see, okay, if I'm doing something on this order, will I get numbers on a similar timescale as this? Which is kind of like the purpose of just understanding it, right?
I think that's a good place to stop the episode.
I think that's good. Again, we didn't talk about the virial
It's
theorem,
fine,
which
it's
is one of the
fine.
most
We can talk about it
fundamental
later.
things, but we cannot do it in the next 2 minutes. So
Yep.
we have already, wow.
I
it's
hope you enjoyed
Yeah.
this episode on
do hope you
astrophysics. We
I
talked
think
about
we
a lot
enjoyed
of
it.
stuff.
I think I
was
enjoyed
a
this
very good
episode quite a
episode.
lot. This was fun.
Yeah. If you did enjoy it yourself, make sure to leave a like. Make sure to rate this 5 stars on Spotify
Yeah.
and Apple Podcasts. You can do that also.
Why not?
Leave a review. I don't know. Subscribe to us on YouTube, and share this with your entire family. Thank you very much. This has been episode number 98 of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we shall see you soon.
Bye, guys.
Take care.